Right. So the insert, for the first thing is that we have to be able to insert this, right? Insert operation we have to look into. Okay. So insert operation, here already we utilize the recursion. How we know that? You see there, so there is an escape routine here, right? Escape routine. And within side of this insert means that the same function was used here, but with the reduced parameter by reducing it to the right hand side or the left hand side. Okay, so let's look into how it performs. For instance, so let's imagine we have to insert these numbers of these numbers into the tree structures. Okay, then let's insert 3, and we don't have a root yet, right? So we are going to put 3 at the root, and then after that we have the empty left hand side and empty right hand side, and then we have to insert 2, and it's only be accessible through the root, so we have to hit the 3 first, and then we have 2. Means that these 2 should be somewhere in the left hand side of this root node, because the rule of thumb of the binary search tree is that the lesser number should be in the left hand side and bigger number should be in the right hand side, right? So here if the value is smaller than the value to insert, right, value is smaller than the value right here. Okay, sorry about that. If the value is larger, if this value is larger than the value to insert, which is equal to 2, which is equal to 3. So perfectly this case. In that case, if there is a node in the left-hand side, LHS, then move to the left-hand side. If there is no node in the left-hand side, so we are in this case, right? No node in the left-hand side, create a left-hand side node. Create this node, and with the value to insert here too. That's happening where? Here, right? So we are setting the left-hand side node with this new instantiated node, right? And this is the value to insert, which is in this case 2, right? So we have 2 here. And after that, we hit 0, right? And then 3. So it means that we have to go to the left-hand side. Here, luckily, if there is a node, here there is a node in the left-hand side, LHS, and then move to the left-hand side node. So we move to here, and then compare it again, and 2 and 0. Still 2 is bigger. It means that we have to go to the left-hand side, but we are hitting this condition again. We don't have the node in the left-hand side. It means that we have to create a node of the left-hand side with this line, right? In the previously, in this 3, moving 3 to 2, that was this recursion, right? This recursion. And after hitting this recursion, we are at this moment, at this moment, and then means that we are hitting these terms again. So we have to create the left-hand side again, and means that we have to create the left-hand side with the value of 0, right? So here we are going to have 0. And then we have 5, right? And 3. And then 3 is actually, the value is smaller than the value to insert. So this is so in this case. And we want to go to the right-hand side, right? So 5 is bigger, so we have to go to the right-hand side. Means, but the problem is that there is no node in the right-hand side. Means that we have to create node with this operation. So we are going to create the right-hand side node with 5. All right? And then what we have to do next is that 7, right? 3 is smaller than 7. So it means that we have to go to the right-hand side with this routine, right? We have to do the recursion, going to the right-hand side node, right? And then in the right-hand side, so 7 is still bigger than 5. Means that what we have to do is that we have to create the right-hand side node, right? So we have to create the 7 like this, right? And then we have 4. So we have 3, right? 3, and then 3 is smaller than 5, means that we have to go to the right-hand side. And then again, we have 5. Here means that 4 is smaller than 5, means that 5 is bigger than 4. So we are hitting this case, right? And then here in the left-hand side, we don't have any node. We want to move to the left-hand side because 4 is smaller than 5, means that 4 should be in the left-hand side of that 5. It doesn't have the left-hand side. It means that we have to create a left-hand side node called 4. So after inserting these numbers, we are going to get this structured binary search tree, right? Let's find out whether we inserted correctly or not. Okay, so all right, and then let's move it out. So we are inserting 3 here, and then after that 2 should be in the left hand side, and then after that 0 should be in the left hand side, and 5 should be in the right hand side of this 3, and 7 should be at the 5's right hand side, and 4 should be at the 5's left hand side. So this is the result that we get after the insertions of this sequence of numbers, right? Okay, so this is a recursion that performs this insertion. Remember that we have this escape routine, and besides of this escape routine, we have this recursive calls here, right? And after that, we have the search operation of binary search tree. Okay, after inserting these numbers, we have to be able to search a particular number. So for instance, let's imagine that we are trying to find 4 in this binary search tree. And this tree has only access to this root node. It means that we have to search from the root by calling get left hand side or get right hand side or get left hand side or get right hand side, right? Right. So we are trying to find 4 from this tree, and the first node stores 3, means that it's not equal, right? It's not equal. That turns out this is becoming 4 going false, right? Means that it has to run this case, and if 4 is bigger than 3, right? It means that 4 must be somewhere. If there is any 4 should be somewhere in the right hand side of this 3, right? And because of that, we are calling get right hand side, and this search operation keep coming. So this is another recursion. So it's keep recursive idea, right? For instance, 4 should be in the right hand side of this tree, but right hand side is empty. In that case, there is no 4 in these tree structures. 4 should be in the right hand side of this tree, but 3's right hand side is null. There isn't any. It's empty. Right hand side is. In that case, yes, this 4 is not in the tree structures. If there was 4, the right hand side shouldn't be empty, right? So let's move to this right hand side node and keep searching with recursive calls. And we have 5, right? And 4, we have we have 5 here. We are keep searching 4. We have 5 now. Means that we have to use this else statement, right? We have to go to this else statement, and then what you have is this. In this if structures, we have to go to the left-hand side because 4 is smaller than the 5. It means that we have to go to the left-hand side. And if the left-hand side was not storing anything, it means that 4 is not in these tree structures. If this tree structure didn't have, this left-hand side node, then it means that it doesn't have 4. However, it does have the 4 left-hand side. Means that we have to continue the search by going to the left-hand side, right? So we are now here at the with the number 4 in the left-hand side, right? And then we have 4 searching value 4, and this node's value is 4, so it searches true, and then it returns, right? So please note that we were using this left-hand side and right-hand side rules to find out to limit the search scope. So when we decided to find 4 here, and when we hit 3 at the root node, we instantly find out that we don't have to search through in the left-hand side of this tree. So we only limited search space to the right-hand side. And then when we hit the 5, we only cared about the left-hand side of the 5 because we know that this 4 is never at this 7, the right-hand side of this 5, right? So what we actually searched through was this area, right? This area. And this area was forbidden in terms of the search. And that was the passage of our search operations, right? So I'm gonna erase a little bit, but this is an important operation. So I'm going to do another iteration of search. Let's imagine that we are going to find out 6. Yes, it is. There isn't any 6, and what we want to find out is that whether we can find out we don't have value 6 in these 3 structures or not, right? Let's do this search operation in these 3 structures. Alright, so we want to find 6 and we hit 3 here. Means that we still have to go to the right hand side, right? And then that's coming from what? Here, this recursive course enables all this. And then still 6 is bigger than 5. It means that if 6 was here, it should be in the right hand side. It means that we have to go to the right hand side for the search. Still, by this recursive course, this was enabled. And 7, we have 7, and 6 is actually smaller than 7. It means that if 6 was here, it should be in the left hand side of this 7. So it means that it should be somewhere here, However, the 7 does not have the left hand side. Means that it doesn't have this left hand side. This can be checked out. This is empty of nodes left hand side. It's actually true. Then means that the search operation actually failed by this findings, right? So this is how you navigate through this binary search tree to find out a certain value, whether there is or not, right? Okay. Right. So let's move on. Before that, finding 4 is actually this root of this passage,